If you would recall, we've been finding and classifying critical points for functions of two variables. We have really just been doing the same thing that we did before. Take the first derivative, set it equal to 0, and solve to find the critical points. Take the critical points, plug them into the second derivative, and check their sign to see if to classify them as a local minimum, a local maximum, or neither. The same thing happens with a function of two variables. If our second derivative test returns a value of 0, then we don't know, and we have to do something else. But it's going to be pretty reliable. It's going to be fairly reliable for most of the problems that we encounter, specifically because most of the problems you encounter will be built by design to work. Kind of like the factorable polynomial thing. So if you recall, we built this function called capital D, which involved all four of our second derivatives. So capital D was fxx times fyy minus the square of fxy then our test is based on two things. If this function D is positive and fxx is positive, then that's telling us concave up and we have a local minimum. So there's four parts. D is this combination function. It's actually the determinant of a particular kind of matrix involving derivatives. I call it the function D because it's determinant or discriminant, and I will just switch between those two words randomly, and so I'm just calling it the function D, so I don't have to worry about messing it up. That's called a workaround. Question? So if the D is positive and fxx is positive, then we have a local minimum. Remember, local minimum is when we're thinking concave up, when we're thinking second derivative is positive. But second derivative positive, there's four of them. So second derivative positive is a little bit different. So this means that we have to have not just this fxx second derivative positive, but also this combination second derivative is positive. So this mirrors the concave up. But it's these two things, D is positive and fxx is positive, where we're saying the equivalent of concave up. And I'm going to put that in quotes because I'm just referencing our original Calc 1 interpretation of things. Because we haven't talked about what concavity would be like on a surface. It probably just means this, right? But that's what we're relating it to. So if you're going to come at me in the comments and be all pedantic, that's why I turn comments off. That's why I put this in quotes. We're trying to relate it to the familiar. But these two things are required for us to make this concave up determination, where before we just had one second derivative. If it came out positive at the point, concave up. Then the concave down case, it's in quotes again, don't at me, is when D is positive and fxx is negative. That's when we conclude local maximum. So here we're kind of grabbing two things. We've still got that second derivative is negative to say concave down, but the D function still has to be positive for us to make this conclusion. So that looks a little weird. Our second derivative negative, concave down, but this d function needs also be positive, and the fxx needs to be negative for us to say concave down. Yeah. This comes from a determinant of a particular kind of matrix. So it is just a determinant, and the determinant is of a matrix. The form of the determinant. See, I need this line, I need this line. Let's put it down here. The determinant has fxx multiplied by fyy, and then minus fxy fyx. Where each row is a different determinant, a different derivative. All these d words, it's a different derivative. So we have the first row is our fx derivatives, and then our second row is our fy derivatives, and then our first column is derivatives with respect to x, second column is derivatives with respect to y. I may have the mixed partials mixed up, but they're the same, so you can be lazy about that. But there's a particular kind of matrix that we'll build when we have all these extra derivatives running around. And for some reason, this determinant is helpful in classifying our things. So that's where it comes from. The natural question is, why does it come from that? And my answer is, so let's move on. So they don't allow me to carry smoke bombs anymore. Right? So some students will be like, well, yeah, but where does that come from? Well, it's an interesting story about that. And then I like disappear. But I have nowhere to go because I'm like trapped behind here. So I'm like, oh, interesting. So I throw the smoke bomb and I actually just climb into this cabinet down here. And so it's like, oh, wow, where did he go? And those students are like, oh, well, he's probably in the cabinet. It's because this is a math class, not like a magic show. Like if it was a magic show, people would just be like, oh, neat. But it's a math class. It's like, oh, no, dude, we had questions. Get out of the cabinet and answer our questions. So I'm just going to tell you, it comes from this kind of matrix, but we haven't got to the point where we need to discuss this kind of matrix. So right now, it's because I said so. There are lots of different matrices that are named for people, like Jacobian matrix, Hessian matrix, and I can't remember which one is which because I haven't had to remember for a very long time. All right. So the other case, skip a line because we want to point out this d positive thing, because the next part is where we get d equals negative if d is negative. If d is negative, then we don't even worry about it. We just immediately conclude we're dealing with a saddle point. If d is negative, then we conclude saddle point. And if d is equal to 0, just like our other second derivative test, then we got to do something else. In this scenario, we don't just get to say no conclusion. We've been asked to classify the critical points. Our job is to classify the critical points. This just means that the second derivative test doesn't work, and we have to go do something else. Like if I give a test and everybody in the class gets 100% on the test, then that test didn't work. That test didn't do anything. It didn't do what it was supposed to do in the traditions. It's also important, if you give a test and everybody gets 100% on it, you do have to make a more interesting test because you've learned nothing. You've essentially learned nothing. Everybody gets 100, you get a 0. Kind of like the inverse of what we got going on here. What I want to point out is the sign of this function d, and we want to look at how d is constructed and then see why the d is positive for the local maximum and minimum, and we base that decision on what fxx is doing. So it comes down to this. If d is positive, when d is positive, if we look at how this is constructed, I've got fxx times fyy, and then we subtract the square of fxy. So whatever fxy is doing, that term is getting squared. That term is positive. And we're subtracting from fxx times fyy. So if d is showing up with a positive number, that means fxx and fyy have the same sign. So d positive means that fxx and fyy have the same sign. Yes. We could have phrased this if d is positive and fyy is positive. So because they have the same sign. If d is positive, xx and yy must have the same sign. That's why we only need to check one of them. So they have the same sign, so we only need to check one of them because they have to match. And second of all, it's like we're looking at the fxx direction, the fyy direction, and saying concave up in both directions. So they have the same sign. We only need to check one. That's why we only need one. And the other thing is, we can think of it as concave up in both x direction and y direction. Or concave down in both directions. That's where we're only checking half of it. Looking at the value of d, that's telling us both of them. If d is ending up positive, fxx and fyy must have the same sign. That's why I'll need to look at one of them. If d is positive and fxx is positive, that must mean that fyy is positive as well. So really what we're thinking of is concave up in the x direction and concave up in the y direction. That means we're going to have a local maximum. If d is negative, the most likely cause for that is especially since we're making this conclusion. So we're talking in circles a little bit here. But if d is negative, One cause of that would be that fxx and fyy have opposite signs. If fxx and fyy have opposite signs, then this first term is going to be negative, and then we're going to be subtracting some more. So that's just going to make it more negative. So this d negative part I forgot I wanted a line in between here, so I have to go up and around. Most likely D is negative because fxx and fyy have different signs. So that would indicate that we're concave up in one direction and concave down in the other direction, and that's what what a saddle point looks like. So I'll have concave up in one direction. And concave down in the other. So one direction will be going concave up. It's a critical point, so we know we're going to be flat in that direction. And then we'll have concave down in the other direction. And just like with our second derivative test from before, if our second derivative is 0, then we have to do something else. We're going to have to look at be more specific about look at something else about the behavior near that point. It could go either way. We could be looking at an inflection point, or we could just be looking at a point that's really flat. So think about x cubed and x to the 4th. Both have second derivatives of 0 at 0. One thing that we should think about, could it be that fxy, because we have fxx times fyy, then we're subtracting the square of fxy. Could it be that fxy is so big that even though xx and xy have the same signs, we're subtracting so much we end up negative anyway? Could it be that fxy is so big that d ends up being negative? So there is another thing that we should think about. But before we get to think about that, let's worry about the main things that happen. Any questions? That's like a 4 asterisk. I don't know if when we stack the asterisks up, stars. I don't know if we put 4 stars, is that 4 star or is it star to the 4th? Yeah, the question is, are we multiplying these or they added up? It's just juxtaposition, so maybe we should read this as maybe this is not correct. Maybe it's star to the 4th. I don't know, that looks terrible as well. I don't know. Also, because just because it's juxtaposition doesn't mean that it's necessarily multiplication, right? That's just the most common thing that we do. Like if I write the number 5 2/3, all we do is just stick the whole number next to the fraction. But what's the operation in between those two? It's addition. It's not 5 times 2/3, it's 5 2/3. So here we're just cramming things together, but we mean plus. So I don't know. It could be 4 star or it could be star to the 4th. That's going to bother me for a while. So we started having different symbols, like that little dagger symbol and stuff like that. Maybe I should have done that. Should have just gone to a different symbol. Clearly, things will get weird if we have complex numbers, but that's a whole separate class. You don't get to do calculus with complex numbers until you get to like upper division math, complex analysis. Any questions? First stage is just being able to use the second derivative test to classify your critical points. That's just mechanical. Second stage is understanding where this comes from and why it works the way that it does, how it's similar to what we've done in the past, what we've had to modify to use it in our new environment. How's everybody, okay? Easy enough? I can't remember which one of these shows up on the homework, but I wanted to do this one because it do some interesting stuff. Mainly because there's a mechanical thing that we don't spend a lot of time on in our algebraic history. Question is the same question as we had for the last 4 days. I know yesterday we didn't have any questions, but same question we've had for the last 3 days of class. Find the critical points and classify them. Now, remember, the first stage is we take the first derivative, set them equal to 0 to solve. That creates a system of equations. In this case, we're going to end up with a nonlinear system of equations. And we don't have specific techniques for nonlinear systems. We just got to like do stuff. So let's find our first partials. The derivative with respect to x is our variable. So the derivative of x is 1. Our constant is 8y. The derivative of a fourth, x plus y to the fourth, is 1 x plus y to the third. Times the derivative of the inside, which is 1. And our first partial with respect to y. Same stuff happens, similar stuff happens. So our strategy is to take these two first partials, set them equal to 0 to solve the resulting system of equations. So this equals 0, this equals 0. And everybody equals 0. Our system of equations. Our strategy for solving systems of equations, one of our strategies is substitution. Solve for one of the variables and plug that into the other equation. Problem here is solving for one of the variables is going to be a mess, because I don't just have one instance of the variable. Solving for x or solving for y in either one of these equations is going to be kind of messy. But when we say solve one of the equations for one of the variables, we get to decide what that variable is. And in this problem, I want that variable to be x plus y to the third. I'm going to solve this the first equation for x plus y to the third, because it doesn't have to be just x or just y. Solve for something that the equations have in common. We're updating our solving systems by substitution. Instead of solve one of the equations for one of the variables, solve one of the equations for something they have in common. That's the evolution that we have today. So I'm going to take this first equation, and it's going to tell me that x plus y to the third is equal to 8y. We don't have to solve one of the equations for one of the variables. We'll solve one of the equations for something the equations have in common. That's our substitution strategy. Solve one of the equations for one of the variables. We're updating that. We get to decide what's variable. Solve one of the equations for one of the things the equations have in common. And that's the point of this particular example. So what we're doing is we're solving for that x plus y to the third because it's common to both the equations. If the x plus y to the third in the second equation was a different power, then I could still just solve for that base, x plus y. That's what they have in common. Because now if I take this, I can replace x plus y to the third with just 8y, and we'll find out that x is equal to y. So this x plus y to the third goes into the second equation. And this equation becomes 8x minus 8y equals 0. Which will tell us that x equals y. Now that I have that x equals y, I can put this into one of the equations, or both of the equations, because the equations are so similar. Combine equations to get rid of variables. That's our strategy. So now we see we have 3 critical points. Any questions so far? This wasn't a calculus thing that we had to do. We had to grab an algebra thing, but it's an algebra thing that we hadn't technically been trained on, solving nonlinear systems of equations. But at this point, we have enough mathematical or algebraic intuition that the whole point was just do something. Y plus y turned into 2y, and then 2y got cubed. So here I've got y plus y is 2y, but then that is cubed, and that became the 8y cubed. How's everybody okay? Now you see the level. Once you see that, you can see the level of control that we have over this problem. We know that if we got this term x plus y, and we're going to make the x plus y thing into a 2y, that means I'm going to want that coefficient 8xy, so that I could factor out the 8xy and have like nice integers. So if I wanted to redo this problem, make it look like a different problem, I would just change the value of this 8. But unless I was being mean, I wouldn't change it to like 9 or something like that, where you have like some weird fractions, some weird positive and negative square roots, right? So I would probably, since I want to be able to factor it out, I'd want to leave behind like a 4 minus y squared, so I have a plus or minus 2. So if that's going to be a 4, I'll make that a 32. So we would see these weird jumps, but I would want a square multiplied by 8 because I know this 2 is getting cubed. I think that is a thing that I came to notice because I come from a time when learning math was in problems 1 through 1,000, do this thing over and over again. What problems 1 through 1,000 involved 3 different skills that were just drilled into me. All right, so when I started this problem, I knew it wasn't going to fit on this half of the page, but I kept writing on this page anyway. I'm not even, because if that's a holdover from like I used to use paper in this process, and I want to be efficient about using the paper. But now I'm going to be like cleaning this. So anyway, I need some second derivatives. Fxx. So fx is 8y minus x plus y cubed. So 8y is constant with respect to x, so the derivative is 0. The derivative of minus thing to the third is minus 3, that thing squared, times the derivative of that thing. Fxy, since I need one of the mixed partials, the derivative of 8y with respect to y is going to be 8. And symmetry strikes again. So the derivative of the minus x plus y to the third with respect to either variable is going to be 3 that thing squared times 1. So symmetry strikes again. Fyy is also just going to give us negative 3 x plus y squared times the derivative of the inside, which is 1. We want to check these at each of our points, but we have a pretty big advantage here. Notice that fxx, whatever we plug in, is going to be either 0 or negative. It's going to be 0 at 0, 0, and it's going to be negative everywhere else, because the x plus y is getting squared and then multiplied by negative 3. So we notice some stuff right away. Fxx at 0, 0 is equal to 0, and fxx is going to be negative everywhere else. Because it'll be negative 3 times a square. That's negative. Same thing for fyy. At 0, 0, we'll get 0, but fyy at xy will be negative everywhere else. When we go to build our function d, I'll have fxx times fyy minus the square of fxy. Notice that this term has fxx and fyy will have the same signs, except at 0, 0. We'll have 9 x plus y to the fourth. So here's our function D. I simplified it for some reason. I think I just missed algebra because we don't do algebra anymore. Now we'll just plug in our 3 critical points. We plug in our 3 critical points, and that will allow us to classify our 3 critical points. Oops. I'm rushing through things and making mistakes. D is positive, fxx is negative. Negative is a local max. Is that what I had before? I can't remember all the way back. It was like 15 seconds ago. Questions? I think smiley face is 128. 48 twice is 96, twice again is 192, right? Minus 64 is 130, negative 2, 128. Any questions? So this exercise was a standard deployment. First derivative equals 0, solve, plug into the second derivative. The weird thing that happened in this problem was the substitution, solving for x plus y to the third, instead of just trying to solve for one of the variables. That's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing. Sorry for running over.